Hi guys, in this video we are going to talk about automatic differentiation VI, ADVI for short, or ADVI. And in my opinion, it's another form of stochastic variational inference. A bit of a notation change. So until now, we mostly followed this paper, which used Z instead of theta. But now we are going to follow this paper, which uses theta instead of Z. And also we use theta to parameterize Q. So now we will parameterize Q by phi. So long story short, Z becomes theta, and what used to be theta now becomes phi. Okay, just a bit of a notation change. So until now, we were mainly focusing on the exponential family, but now we are moving to a general case problem. So ADVI is applicable to any type of problem. Let's give a brief outline of ADVI. So we first have to transform the thetas to being non-constrained so that they live on the continuous line. We'll denote this by xi. Okay, so we take the thetas, the quantities that we were trying to find a posterior of, and if they are constrained, for example, as I will show here in the Poisson distribution, the theta has to be above 0. We will take some transformation of it such that it's now unconstrained. In the unconstrained space, we will use a variational family of Gaussians. So in ADVI, we only use Gaussians, not anything else. There are two types of Gaussians that are discussed in the paper. One is the mean field Gaussian, basically a Gaussian with a diagonal matrix, and the other is a full rank Gaussian. We will transform the variance parameters of these Gaussians to also be unconstrained. And now we will do stochastic gradient descent. We will have to compute the gradients for the ELBO. In order to push the derivative into the expectation, like I mentioned in the previous video, we will use the reparameterization trick. In the paper, they call it elliptical standardization. And because we are using Gaussians, this is totally possible and easy. We will simplify the derivation for the general case. We will try to find the gradients with respect to the mu's and the variance parameters of these Gaussians of the variational family. We will only simplify up to some point. At that point, we will move to automatic differentiation, and we will replace the expectations because we pushed the gradient inside the expectation, but we are not really going to compute now the expectation, which is an integral. We'll just use MC integration instead. So first, we're going to transform the variables to being unconstrained. This requires multiplication by the determinant of the Jacobian. Okay, so we transformed theta into xi by some transformation. So theta is the inverse transformation of xi. So we can write now the joint like this. We replace theta basically with this quantity. When we change this in distributions, we have to multiply by the determinant of the Jacobian of the inverse transform. So it looks like this. And yeah, and we can also break the joint into the likelihood times the prior. Note that there could be more than one transformation. And this is something that needs to be taken under consideration. In certain cases, you wouldn't even have to compute this. For example, if you use Stan, it has a library of transformation and their corresponding Jacobians. So giving an example, let's suppose our likelihood is a Poisson distribution. The parameter in the Poisson distribution has to be strictly positive. So we can take as a prior that it distributes by Boole. In order to move to a non-constrained, we need to take the log of it. So if theta is strictly positive, the log of theta lives in R. The determinant of the inverse Jacobian is exponent of xi. So basically, we take the inverse transformation, which is this, and then we take the derivative of this with regard to xi, but this is just, it remains e to the power of xi. So if we now write the joint, it would look like this. We can break it down to the likelihood times the prior times the determinant of the Jacobian. This is one-dimensional, so it's just equal to this. And if I write it also with the actual PDFs of the likelihood and the Weibull prior and the Jacobian, it would look like this. Okay, and this is just a simple graph that they put in the paper. It just shows, okay, here we had it constrained, it had to be above 0. We did a transformation, and now it's unconstrained. How does it affect the ELBO? So this is how the ELBO looked like previously. we are now moving from theta to xi, and we are going to put the q, our q's are going to live in the xi space. Okay, so because they are living in the xi space, we don't have to transform anything for the q, only for the p, x, and theta, because only here we will have the thetas. Okay, so the ELBO becomes an expectation over the different values of xi coming from q of the log joint, and instead of theta, we will use the inverse transformation here times the Jacobian. And again, here we don't have to do this because we pose the variational family already in the xi space. Okay, the log of the product becomes the sums of logs, and that's it. The second term, we are going to break it away from this expectation because it's just equals to the entropy. Okay, so this thing over here, it's equal to this, which is the definition of entropy. And the reason we are doing this is because for Gaussians, as we will see, there are closed form solutions of what is the entropy of Gaussians. Okay, so we reached this far. The question now is which Q we are going to use. And as I mentioned before, in ADVI, we are only using Gaussians. There are two types of Gaussians that are considered in the paper. One is the mean field Gaussian, basically a Gaussian with a diagonal matrix. And the second is the full rank Gaussian. In both cases, the variance parameters are constrained. Okay, so the variance here, it has to be above 0, and we don't want that. So we will also reparameterize to get rid of this constraint. So we will call omegas the log of sigmas, and notice that 2 omegas is actually the log of sigma squared. And now our parameters are basically the mu's and the omegas. So we are now trying to optimize these parameters. Yeah, and a good question to ask is, why are we doing this? So why did we transform the first parameters to being unconstrained? Well, it makes sense. If we are using Gaussians, Gaussians are unconstrained. So we did the first transformation of the original parameters, of the original quantities that interest us, yeah, the variable that we wanted to find the posterior of, because we wanted to find it using Gaussians. But now a question is, okay, why do we care about transforming the sigma squares or the sigma matrix here? And I think the reason is because we are now going to do stochastic gradient ascent. And to do this, we also want it to be unconstrained. So we don't want to do stochastic gradient ascent when there is a constraint on one of the parameters. We move it to being unconstrained, and then we can go freely in the gradient descent without worrying that we reach some constraint boundary. Okay, so this is how it's done for the mean field Gaussian. For the full rank Gaussian, we use the fact that the covariance matrix is positive, definite, and symmetric. So we can use the Cholesky factorization. And then L, which is a lower triagonal matrix, the elements in that matrix are unconstrained, and it can be any number. So the mean field Gaussian, let's say in 2D, can only be something like this. Yeah, it has to be like axis aligned. And the full rank Gaussian, it can be also something like this. Yeah, it can capture these angles. Yeah. So obviously it's more expressionate than the mean field Gaussian, but it also comes with a computational cost. Okay, and because we are using Gaussians, then the reason why we separated the entropy here becomes clear. There are closed form evaluation of the entropy and its gradient. So the entropy of a normal distribution looks like this. For the mean field, if we calculate it, we arrive here. For the full rank, we just replace the sigma with the LL transpose. Now the derivatives of the entropy with regards to the parameters that we are interested, the parameters of our variational family. So again, the parameters are the mu's and the sigmas, yeah, and the variance parameters. So with regard to mu, it's 0, right? This does not depend on mu, and neither is this. With regard to sigma, well, the sigma here are the omegas in the mean field. So taking the derivative of this with regards to omega just gives a vector of 1. And taking the derivative of this with regard to the L matrix, the lower triangle matrix, in the paper they state it's equal to this. I tried to check this. It seems to be right, but the math is really, really hairy. So I will leave this out of the video. Okay, so now we know what the entropy is and the derivative. and we also transformed the Gaussians. We now want to do stochastic gradient ascent, which is basically this. You update the value of your parameters to what they were before, plus a step, which can be also adaptive. It can also depend on t, times the gradient of the function you are trying to maximize. As we saw in the previous video, it's better to do the reparameterization trick than to do reinforce or the log derivative trick. And since Q here is a Gaussian, we can do the reparameterization trick. So why do we want to do the reparameterization trick? Again, it's to push the gradient into the expectation. Yeah, so the ELBO is an expectation of something. We want to just push the gradient inside the expectation and then use MC integration to calculate this quantity. So what is the reparameterization trick? Well, it's basically just standardizing the normal distribution here. In the paper, they call it elliptical standardization, which I guess is the special case name of the reparameterization trick on Gaussians. So how does it look for the mean field? For the mean field, you just take away the mean and divide by the standard deviation. So it's like this. The transformation in vector form would be written like this, and the opposite transformation would look like this. For the full rank Gaussian, it means take the vector of Xi, subtract from it the vector of mu, and then pre-multiply it by the inverse of the L matrix. And this will give us a standard multivariate normal distribution. The opposite transform would be written like this. In both cases, we get that the new quantity, yeah, so we moved from Xi now to eta. So the new quantity, the distribution of eta, is standard normal with 0 and an identity matrix, which can also be factored into the product of the individual dimension standard normal in 1D. What happens to the ELBO? So instead of Xi, we are now writing the inverse transformation of eta. Notice that the inverse transformation does depend on the parameters, right? So this inverse transformation, it has the mu's and it has the omegas for the mean field, and it has the mu and the L for the full rank. So it is depending on the parameters. And so is the inverse transformation. The inverse transformation still has L and mu, or omega and mu. So these quantities over here, which we use to replace the Xi, they will still depend on eta. But notice now the expectation is with regard to a standard normal distribution, which is important. And here again, the product becomes the sum, and we are left with this term. Now, we should have also multiplied by the determinant, right? Because we did another parameter transformation. The paper states that the Jacobian of the elliptical standardization evaluates to 1. I'm not sure what they meant with this. The Jacobian is obviously not 1. Okay, the Jacobian for the 1D case, for example, is equal to the standard deviation. For the multivariate case, it's equal to the square root of the covariance matrix, which we could say it's equal to L. I guess what they meant is that the determinant of the Jacobian is canceled with the determinant of the Jacobian inside the PDF. So this is a PDF in 1D of normal distribution. If we now take the expectation of some function with regards to this, and this function can be what I wrote here, right? So before we change from Xi to eta, we had this thing, and now we change to eta. So this becomes eta, and Xi becomes this thing. We have to multiply by the determinant, but then it cancels out with what's here. Okay, and it also happens for the multivariate case. Okay, so these two cancel out. We are left with the PDF of a standard normal distribution times this function. So it becomes this. So this is why we don't have to multiply by the determinant here. You can think of it as if we multiplied and then it got canceled away, and now we are left with this thing over here. Okay, since the expectation is no longer dependent on the parameters, on the phi, we can push the gradients with regard to phi directly inside the expectation. So now we have an expectation over these etas, which distribute standard normal. We know how to sample them, so we will just sample them now, and we'll calculate the derivative of what's inside. So this is what we got, and now we are going to simplify or just derive a little bit more. What are these derivatives with regards to mu and with regards to omegas or L, yeah, the variance parameters? Because we are going to use the chain rule, I'm going to switch these notation. Yeah, so this is xi. So I'm going to write it as xi as a function of eta, and this is theta. So I'm going to write it as a theta as a function of xi as a function of eta. So this is to help us when we're doing the chain rule now. So if we take the derivative with regards to the mean, we saw that in the entropy, everything vanishes because the entropy doesn't depend on the means. So this term cancels. We take the derivative of this with regards to the mean and of this with regards to the mean. Using the chain rule, we transform it to this. Notice that this cancels away because xi is just this. When we take the derivative of this with regards to mu, it just becomes 1. Okay, so we are left with just this expression over here. So this is as far as we are going to derive for the means. For the variance parameters in the mean field, we saw that this term over here is equal to a vector of 1. We do the same thing over here. This time, this quantity is equal to this thing over here, right? Because we are taking the derivative of this with regards to omega. So it's just equal to this thing over here. And this is as far as we are going to get with the mean field omegas. For the L, we do the same thing. We saw that this is for the entropy. The derivative of this is just eta transpose. And this is what we get for the derivative of the full rank version of the Gaussian. So we reached here, but from this point on, we will use automatic differentiation. Automatic differentiation leverages the fact that every expression, every function, when we take the derivative of, is made of elementary arithmetic operations. Yeah, so this thing could maybe be a really complicated function of theta, but if you break it down to the simple operation, well, it's either a plus, a minus, a product, a quotient, or an elementary function that applies over it. Yeah, like a sinus, a cosinus, e to the power of, log, etc. And each one of these operations, you can calculate the derivative of. So for the product, you have the product rule. For the quotient, you have the quotient rule, etc. So you can create this mapping and then map every operation to the relevant derivative of that operation, and that way calculate the derivative of it. And so there are efficient programs that already apply this. So you give it some function, you define the functions, and then it automatically gives you the derivative. So the only thing left now is to do the MC integration. We can now calculate everything inside the expectation as long as we have some value of eta and we have our data. Okay, so if we have some value of eta, let's say eta 1, we can use it to find the xi. We can use the x's to find the theta. We can use the automated differentiation function to get the functional form of this and the functional form of this, place the values of the x's or thetas in them, and calculate the number. Yeah, we will get some number or vector of numbers. So this is exactly what we will do. We will sample etas from the standard normal distribution, and usually we will sample one observation. We will convert the eta to xi using the current version of the parameters, right? So we have some current version of the parameters, and we will use them to calculate the x's. Then differentiate the quantities over here that are dependent on the x's. Yeah, so here the Jacobian, as I said, Stan, for example, already has this Jacobian for you, so you don't have to calculate a lot. We will take the derivative of that with regards to xi. We'll transform xi into theta using the inverse transformation, and then take the derivative of these quantities over here with regards to theta. This will be our gradient. We'll take this big of a step into that direction. And this is basically gradient descent or stochastic gradient descent due to the MC integration. Okay, the step size is also adaptive. It depends on t, but I won't go into this right now. So what are the pros of ADVI? It's a general purpose stochastic variational inference algorithm. It's easy to use. What is the con? Well, it's too simple. We are only using Gaussians, and this is very limiting. So Gaussians are unimodal. So even after the transformation we will make, whatever distribution that we will get will also be unimodal. There are papers that came out later, and it seems that they try to do ADVI for more expression and distribution. For example, I saw a paper that tries to do it with GMMs. Yeah, and maybe I should note that I think that the reason they used Gaussians is because they wanted to do the reparameterization trick. Maybe also because it's more simple and the derivation is easier. But I think the main point is that they wanted to do the reparameterization trick to push the gradient into the expectation, because in another type of a general purpose algorithm that we will see in the next video called black box variational inference, they didn't use Gaussians. And so they didn't do the reparameterization trick, and they had to do the log derivative trick. So I believe that the main reason that they chose Gaussians is because they wanted to do the reparameterization trick. So the restriction is not necessarily to Gaussian, it's to any distribution where you can do the reparameterization trick. And again, there are papers that came later that tried to do ADVI, that tried to kind of stretch the reparameterization trick to other distribution. So this is all for this video. I hope you enjoyed, and see you in the next one.